Hello, welcome to the talk. I'm Nurul Lubis from Heinrich Heine University, and today I'd like to share our work, Dialogue Evaluation with Offline Reinforcement Learning. If you've worked with dialogue systems, I'm sure you've struggled with the topic of dialogue evaluation. For the longest time, dialogue evaluation was focused on user-centered criteria, where the system interact with the user and user give the feedback about the system afterwards. Unfortunately, this is very time and cost intensive to perform, and it's difficult to replicate for comparison purposes. Researchers then resort to a user simulator in place of a human user. However, developing such simulators is far from straightforward. An alternative is corpus-based metrics, but they don't always align with human judgments. More work and strides toward better metrics are focused more on subjective qualities, making it more suitable for chat-oriented systems. For task-oriented ones, success rate measures whether the system successfully helped the user fulfill their goal through the interaction. A common benchmarking is the multi-was corpus, where corpus-based success rate is computed based on pseudo-dialogues, where the user turns are taken from the corpus, and system turns are generated. We then use a script to check whether the system generates the requestable tokens that are present in user goal. The advantage are this is very practical, easy and fast to compute. It also provides fair comparison that's suitable for benchmarking. This leads to its wide adoption for policy optimization works in the past few years. However, it is important to ask, how well does this actually reflect system performance? We see that this pseudo-dialogue contains context mismatch, and this emphasis only on requestable tokens may lead to exploitation when we optimize with reinforcement learning. All in all, the challenges we see in evaluation is well summed up by the recent NSF report. We have metrics that are focused on limited subjective qualities, there's lack of generalization, and not yet a significantly strong correlation with human judgments. In this work, we aim not to only answer these challenges, but also to come up with an efficient and reliable method to evaluate dialogue systems. To this end, we propose to use offline RL critic as dialogue evaluator. To train an evaluator with offline RL, we need only a static dialogue dataset. From the dataset, the critic takes state action pairs, S and A, to produce its estimate, for example, Q value. During critic training, this estimate is refined by iteratively minimizing the error of the Bellman equation, which states that Q value of time step T is equal to reward at that time step plus discounted Q value of the next time step. The beauty of this is really that each of the components are ontology, data, and model independent. We can take any definition for state, action, and reward. It is also theoretically grounded. Instead of pseudo-dialogue, the context is now taken care of by the Bellman equation. Traditionally, with offline RL, the critic's estimate is then used by the actor of dialogue policy as the reward for optimization. For dialogue system, we can start with supervised learning pre-training and then continue training with offline RL, where we interleave actor and critic training them at the same time. In this work, we propose to use critic in a new way as dialogue evaluator by training it independently after the fact. This allows comparison with a wide range of systems. We simply use the policy which we want to evaluate as the fixed target actor during critic training, and then use the final critic to estimate the Q values of that policy over a test set. So, can the critic optimize the policy as measured by established metrics? Based on corpus-based and interactive evaluation, yes. Compared to a model that's trained only with supervised learning, shown in light blue, task-related metrics are consistently improved by using offline RL on critic signal. In terms of evaluation, we take 4 systems with varying models and training algorithms, and we compare these models based on various metrics. First, we take a look at the corpus metric from multi-was. Based on the match and success rate, Lava KL is shown to be the winner here. This is not surprising as this model is optimized with RL exactly on this metric. When we look at BLEU, a model called HDSA is the winner. This is because this model is trained with strong emphasis on response generation. On the other hand, our critic shows that our GPT has the highest Q value, followed by our model, which is optimized exactly on this metric. We see that the result can be quite different depending on which metrics we look at, and it can often be explained by how the systems are optimized. When we see the result from the interactive evaluation with both user simulator and human trial, we get different trend altogether. Our GPT does very well on interactive evaluations by a large margin, followed by our model. This is unsurprising as our GPT uses large pre-trained model with data augmentation, unlike other models that we compare with. We can see a better picture once we look at the correlation with human judgments measured with Fly's kappa. We see that standard corpus-based metrics are negatively correlated with human evaluation, which is surprising. We confirm that BLEU has poor correlation, whereas our critic has a strong correlation at above 0.7. With interactive metrics, user simulator is shown to be a good proxy to estimate system performance in human trial, shown by its very strong correlation. Note that although US evaluation provides stronger correlations, our proposed critic has the benefit of being corpus and model independent. In conclusion, in this work, we propose utilizing offline RL for dialogue evaluation, which has desirable properties that work towards solving current challenges of dialogue evaluation. This provides an efficient and reliable metric that has strong correlation with human judgments. In this work, we apply this to task-oriented systems. However, this method can theoretically be applied to chatbots as well, using other metrics such as engagement as reward signal. We'd like to thank our sponsors for funding parts of this work, and I thank you for your attention.